Welcome to Chemistry 112. So, the test is upon us. The test is nigh. You should have gotten an email about it yesterday. Basic idea is it is Thursday evening at 7. I understand not everyone can make it Thursday evening at 7. So with that in mind, contact me, set up a time, come by anywhere between 11 to 3 on most days or 11 to 1 on Friday. So come and take it this week. If you don't think you can make it Thursday, take it a little early. Give yourself a 2-hour time period. Give yourself a 2-hour time period. You probably won't need the whole 2 hours. It's mostly multiple choice. Even the titration problem is multiple choice. So take that with a grain of salt. You still need to know a little bit about the math. I said, go ahead and definitely bring a calculator. You'll need one unless you can do logarithms in your head, which if you're taking the MCAT, you will need to be able to at least approximate logarithms. So that's there for you. But the fact of the matter is, bring a calculator. If it helps you feel a little bit more confident, bring a sheet of notebook paper where you put like a little sheet of notes to help you. That's fine. I'm more about, can you apply what you've learned rather than can you memorize all the particular formulas? Can you turn pH into H? Do you know how to look for, is this an acid or a base I'm dealing with, and thus what do I need to do at this step? So if you want to, for example, a good thing might be to do on that is show example problems where you work out, oh, this is how I do calculate H plus of a weak acid or something like that. Oh, this is how I do a titration problem. But either way, so that is available for you. You'll be taking it in Odom 101, which is the massive lecture hall. They've had some jazz ensembles in there. You'll be taking it with a different chemistry class so as to minimize time waste on my part. So we'll plan for that on Thursday evening. Otherwise, come find me. 11 to 1, I should be in my office unless I'm saying going to make copies or heating up food in the break room. 1 to 3, I should be in the lab area. So you can find me at any of those times there. And so take the test if you can't make it on Thursday. In mind, we'll go ahead and get started by going back to the last year's test. With that in mind, let's go ahead and get started on the we may have already gone through this problem, but I'm going to go through them again just as a quick reminder. How to do KSP. So zinc, carbonate. On this take-home exam, you were expected to look these things up. Easy enough to do. Why don't you, if you Google what they say, KSP values or some other source and find your concentrations. So I need silver sulfide and zinc carbonate. Silver sulfide is, let's see whichever one comes up first. It's alphabetical. Yeah, it's alphabetical. So silver sulfide is 8 times 10 to the negative 51st. And zinc carbonate is 1.46 times 10 to the negative 10th. Just looked that up. KSP values was my Google search, and that's the first thing that came up. Oh. Go to the doc. Okay. So the idea here is on the ice table that you're breaking down zinc carbonate solid. The shortcut we're doing is that because of this, you then the zinc 2 plus and carbonate 2 minus, that this doesn't matter because it's a solid. At initial point, these are 0. So x at the C, and so this is just x, and this is also x. So what does it leave us? Our KSP expression is just equal to zinc 2 plus times carbonate 2 minus, which is essentially x times x, or x squared. So with that in mind, 1.46 times 10 to the negative 10th equals x squared. What are we doing? We're square rooting both sides to solve for x. Solving for x will give us the concentration of zinc and the concentration of carbonate. So all I have to do is say square root 1.46 times 10 root negative 10, and it gives me the concentration that should be 1.2. We'll say 1, 10 to the 2, 4, 10 to the negative 5th. So that's the concentration of zinc. Now, silver is a little bit harder because silver, it's plus 1 and 2 minus. So when we break this apart, Ag2S, what we're looking at is it breaks apart into 2 Ag and 1 S2. The amount of, once again, the amount of Ag2S doesn't matter because it is a solid. However, these both start at 0. Now here's the tricky part. When we break one atom apart, we form 1s, but we form 2 Ag. So when we all said and done, we have 2x and x. And when we write this KSP expression, KSP is products over reactants raised to the power of their coefficients. So Ag, since it's 2, it's Ag squared. And S, since it's S1, it's just S. So when we plug in our 2x, we have 2x squared times x. 2x squared is 4x squared. 2x squared is 4x squared. 4x squared times x is 4x cubed equals our KSP. So KSP, which is, we'll say, as we said, 8 times 10 to the negative 51st, 4x cubed. First thing we have to do is solve for x, and then from there, because I asked for the amount of silver, we have to find 2x. So 8 divided by 4 is 2. And then we have to cube root. Once again, how do we cube root? In this calculator, I can say 3 and then x root something, or I could raise it to the power of 1/3. All those would work. But let's do that. You get x. X is equal to 1, we'll say 1.3 times 10 to the negative 17th. Now 2x then, 2x is just going to be 2 times that number. Oh, geez. And so without rounding, that's like 1, it would be 2.5 times 10 to the negative 17th. Sorry, the light went off. Okay, that's not good. Give me a second. So down dark in here. Okay, but 2.5 times 10 to the negative 17th would be the concentration of silver. Okay, moving right along. Moving right along. Okay. We have another titration problem. This one is a base. It's titrating a weak base with a strong acid. Now, what is the concentration of the base? Concentration of the base we figure out by looking at MAVA equals MBVB. We're given 12 mils of base, but we're not given the molarity of base. We're given that the molarity of acid is 0.15 molar, and looking at where the equivalence point is, we have 20 mils of acid. So we're setting this up. And just to note real quick, so I don't have to switch back, for the pKa equals pH at half equivalence point. Now, typically with a base, you're looking for the Kb. But you can look at, since the Kb and the Ka are directly related, based that 14 equals pKa plus pKb, you can find the pKa because this is a pH titration. So half equivalence point would be half of 20. So what is the pH at 10? That's really close to 11. We'll say 8 times 10 to the we'll say it's 10.8 as our pH at half equivalence point. So with that in mind, 10.8. How do we get the molarity of base? Well, 20 times 0.15. We divide both sides by 12, and that will give us our molarity of base. So don't look an easy problem in the mouth just because it's not multiple choice. 20 times 0.15 divided by 12 is, the molarity is 0.25 molar. Now, since the pH is equal to the pKa, 10.8 is equal to the pKa, but I asked for Ka. How do you get Ka? Ka is equal to 10 to the negative pKa. So 10 to the negative 10.8. And here's where your numbers could differ a little bit, depending on whether you said this was 10.8, 10.85, 10.9. You might get a little bit different number. And there's leeway in this answer. As long as you're not saying, oh, that's 10.2. You say it's closer to 11, but lower than 11. You're pretty safe on that number. Pretty safe. But okay, so that is that problem. Okay, so we gotta moving on. Okay. Okay. Determine the H plus of a 11.4 pH solution of LiOH. This one is set up to be a trick question, but it's not. pH, LiOH. So this is a base. But I'm asking for H plus concentration given a pH. H plus concentration given a pH. The direct relationship is pH as H plus is equal to 10 to the negative pH. Just the same way as OH minus is equal to 10 to the negative OH. So it doesn't matter that this is a base. If I plug this number into this equation, I will give you H plus. 10 to the negative 11.4 gives us the fact that we have very little amounts of acid in this base. Your answer should be 3.98 times 10 to the negative 12. Maybe since this is 11.4, it maybe should even be just 4 times 10 to the negative 12. But I'm not going to be super picky on significant figures. So it's a very small concentration, but that's because this is a base, not an acid. Word document. Once again, these were buffers you had to look up the pKa or the Ka. I didn't give those to you. However, this is a take-home exam. I expected you to be able to look this up. On an actual test, not so much. You'll be given these guys. So on the first case, I gave the 0.34 molar for the dihydrogen phosphate and then 0.84 molar of hydrogen phosphate. So we have the acid on the left, base on the right, or conjugate acid. On the second problem, there'd be 0.353 molar of trimethylamine and 0.72 molar of trimethylammonium. So that would be a base and a conjugate acid. So either way, you would look up Ka values, and let's look up H2PO4 to HPO4. You look that up, it's 6.3 times 10 to the negative 8th. Now, this might differ a bit depending on where your source is. So in this case, I would say cite your source. But in this case, it'll be fine. We don't have to get it exactly what I was going for the test. And the fact of the matter is, you're allowed, as long as you state where you got the number, to use whatever. So I'm going to look, I can't find this really easy. So let's say trimethylamine. And let's see what it has on Wikipedia. Wikipedia is pretty good, honestly, for a lot of these values. There's maybe better values out there, but it will do for us for now. So the they give us instead of the Kb, but the pKb is 4.19. It's the pKb. Okay, I've looked up my values. Time to go to the doc cam. The equation. Basically, what we're doing, we're setting up an ice table. Most times, we're going to assume that we're saying that the ice table, ICE, H2PO4, 1 minus, 2 minus is going to be 0.34. And then we have H plus and HPO4, 2 minus, and that's 0.84. And then we say, oh, that's minus X, that's plus X, that's plus X. And on most occasions, we're going to assume that this minus X and this plus X are essentially 0. We're going to make this assumption to make our lives a little bit easier. So rearrange, so you would have a K that equals what? X times 0.84 over 0.34. And basically what we're doing is we're rearranging this to say Ka times 0.34 divided by 0.84 is going to be equal to the concentration of H plus. And then we're turning that into pH. The other version of this would be pKa plus log of, would be like 0.34 over 0.84 equals pH. Either one will give you the same answer as long as you follow through with the steps. I can do this one, and I just have to make sure to take the negative log later. So if I take 6.3 times 10 root negative 8 times 0.34 divided by 0.84 gives me my concentration of hydronium. Take the negative log of that answer, you would get, okay, This guy has a pH of 7.59. 7.59. Now, that's a really low pH. But that is fine. That is fine. It's a really low Ka. I mean, that's a pH that is almost, it's a little bit slightly basic. Oh, sorry. Thank you. So we have a 7.59. This is actually in the basic territory, but it's not fully neutralized yet. Not fully neutralized. That's the nature of this, because we're getting into downright basic territory at this point. Even though we could lose one more proton, it's going to take a lot of base to remove this last proton. But so we just set up our basic Ka expression. Now, we can do the same thing with our base. The only difference is that Kb would be the OH minus times the conjugate acid over our base. Rearranging that, you would have Kb times the base over the conjugate acid equals OH minus. Alternatively, we would have POH equals PKB plus log of base over acid. So pH equals pKa acid over base, or sorry, base over acid, and POH equals pKb log acid over base. We've swapped them around depending on whether we're getting POH or pH. I'll go ahead and use this version since we already have the pKb that I got from Wikipedia. 4.19 plus log of our acid is 0.72, our base is 0.53. This is going to give us the POH. Our POH, so plus log of 0.72 over 0.53. Our POH is 4.32. 4.32. Now, the last step, and this is where no amount of like cheating or whatever will really help you this if you don't realize what you're doing. If I ask for the pH, you got to recognize since this is a base, this gave me the POH. So I have to take 14 minus this. It's not so easy that you can just like go through rote. You have to at least think about this for a hot minute. This is the base, gives me the POH. I asked you for pH. So 14 minus 4.32 gives us 9.68 is our pH. You have to be able to think that through, reason that out. Expect at least a couple buffer problems. Hopefully nothing too hard, but something like that where you either have to use the K version or the Henderson-Hasselbalch. Okay, this last one is a really long one. Don't expect something nearly so hard. I shortened these down, but you expect at least a little bit of a strong acid titration problem. So let's write all the values down. Oh, what are the titration? So we have a 0.45 molar NaOH titrated with the 25 mils of HBr. And then equivalence point is 19 mils of base. And then I ask you, what is the concentration of acid? Then what is the pH after 0? 10, 19, and 20 mils. Okay, so going from here, the first question, what is the concentration of acid? MbVb equals MaVa. This is Gen Chem stuff that we keep coming back to. So 0.45 times 19 equals 25 times your molarity of acid. 0.45 times 19 divided by 25. 25 is 0.342 molar. This should be an easy question. After 0 mils added, initially, before anything is added, what is the pH? Well, it's a strong acid, so it's just simply log of the HA, negative log of the HA, because strong acid, we assume 100% dissociation. All we have to do is say negative log of 0.342. Negative log of 0.342 gives you a pH of 0.466. Oh, sorry, pH. Now, the first real challenge problem is the first titration of 10 mils. So we're going to do I, C, E. We have our acid. We have our base. And we don't have to worry about the products because the products are water and a salt. Water, salt. Now, the amount of acid will not change. 25 times 0.342 is going to be 8.55. 8.55 is the moles of acid. The moles of base will change. So 0.45 times 10 is 4.5. So acid is in greater amount. So when we subtract out 4.5, the amount of acid left is 4.05 moles, well, millimoles. Now, to calculate pH, we have to take the negative log of HA concentration, not millimoles, but concentration. So we're going to take 4.05 divided by, we had 25 mils plus another 10 mils. Oh, God. Thank you. 25 mils plus another 10 mils, and that gives us 35 mils. So our concentration of HA after the first titration is 0.11, we'll say 6. So it's dropped from 0.342 to 116. So to do the pH, it's negative log of 0.116. So what has happened, it's going to drop, well, it's going to increase, but not by a whole lot. The first titration should not increase it by a whole lot if it's a strong acid, strong base scenario. Now the second part, 19 mils. This one is actually a lot easier if you are clever. If you are not clever, it might trick you for a minute, but hopefully you'd still get it. AH plus, OH minus, because this is still 8.55. However, what is 19 times 0.45? It's 8.55. What happens? Which one's in greater amount? Neither of them are in greater amount. So you have 0 acid, 0 base. These are both strong acids and strong bases. What happens when they cancel out? It is perfectly neutral. So what happens at perfectly neutral? We have pH 7. No other math needs to be done. If you had recognized, and I told you the equivalence point was at 19 mils, you could have just slapped on pH 7. You're done. Now, the last one, I see, we have still 8.55 amount of base, but of acid, but now we've increased the amount of base to 20 mils. So 0.45 times 20 gives us exactly 9 millimoles. Now suddenly it's acid that's in the limiting, and the base is in excess. So when all is said and done, we have 0.45 millimoles of base left. We have to convert that to molarity. So it becomes 20 mils plus 25 mils, or a total of 45 mils. So 0.45 divided by 45. So the molarity of base is 0.01. Molarity of OH. Now here's the tricky part. Negative log of OH minus gives us POH. So if I take the negative log of that, that is not my answer. That is, you'd get a POH of 2. We want a pH. pH equals 14 minus POH. So the pH is 12. 12 pH. So our values are 0.466, 0.936, 7, and then 12. And of course, the initial concentration. As I said, I've done this one up as a multiple choice. Done this one up multiple choice in only 2 parts instead of 4 parts for the exam. You still need to be able to do it, but hopefully it's a little bit easier. Now, the last thing we'll go through is the extra credit. Just because the extra credit is something, expect a few questions like this. It's not hard. In fact, hopefully you'll find it somewhat easier than this titration problem. Classify the following salts as acidic, basic, or neutral. Ammonia, or you could hypothetically have more information needed. Calcium 3 phosphate. Okay. Okay, and then strontium chloride, zinc bromide, and barium sulfate. Okay. Okay, so how do you go about figuring this out? To do this, you would break it down into the cation-anion pair. The cation is responsible for whether it's an acid or not. The base is responsible for, the anion is responsible for whether it's a base or not. So looking at these guys, you break it down into cation-anion pair and look at whether this is mildly acidic or mildly basic. Now, this guy, we have breaking down calcium, strontium, zinc, barium. Now, you have ammonium. Ammonium, is that an acid or a base? And nitrate, is this an acid or a base? Is this a salt? To figure this out, you would add an OH to the acid and say, is this one of my strong, OH to this to say, is this one of my strong bases? If the answer is no, then it is acidic. To the anion, you'd add a proton to this and say, is this one of my strong bases, strong acids? If no, then it's basic. So looking at ammonium nitrate, I put that there, put an OH with ammonium, you would get either ammonia or ammonium hydroxide. Either way, this guy is a weak base, meaning this guy must be a weak acid, mildly acidic. When I put H with nitrate, we get nitric acid. This guy is a strong acid, so this must be a salt. If I have two opposing factors, weak acid and a salt, the weak acid wins. And so this first guy is going to be acidic. Now calcium 2 plus. If I put on hydroxide, we have CaOH2. And phosphate, if I put on that guy, it's HPO4 2 minus. Now here comes a tricky one. HPO4 2 minus is a very weak acid. So this part is definitely a weak base. But calcium hydroxide is not a strong base. If I'm not mistaken, it is maybe a mildly soluble base, if at best. So this might classify as a weak base, meaning this guy is a weak acid. In this case, when we have a weak acid and a weak base, you need to look at the Ka values to determine which one is stronger. On a take-home test, you could look up those values. On an in-person test, if you're not given Ka values, you need more information. There's no way to determine that just by looking at those two compounds. You have to say, well, that's a weak acid, that's a weak base. Which one is stronger? I don't know. We need more information. Strontium chloride. Strontium, you'd get strontium hydroxide. This guy is a strong base. And Cl, you get HCl, a strong acid. Strong base would give us, strong base would give us a salt. A strong acid would give us a salt. And so when all is said and done, strontium chloride is just a salt. Nothing more, nothing less. Zinc bromide. You break that down into zinc hydroxide and HBr, hydrobromic acid. Hydrobromic acid is a strong acid, so bromide is just a salt. Zinc hydroxide is not a strong base. There's only like, say 1, 2, 3, 4, 5, like 7 strong bases, and they all come from the first 2 columns. So any metal, transition metal, is guaranteed to be a weak base of some kind. So that means this, so that guy is a weak acid, meaning this guy is, once again, acidic. And the last one, BaSO4. Ba becomes BaOH2, which is a strong base. But here's the tricky part. It's SO4. If you put 2 hydrogens, it becomes a strong acid. But 1 hydrogen is a weak acid. HSO4 is a weak acid, meaning this guy is a weak base. So the last one was, it ends up being a weak base. So for extra credit, it was acidic, unknown, salt, acidic, basic. But you only have to look at the cation-anion pair. Does this come from one of the like 8 or 9 strong acids? Does this come from one of the 7 or so strong bases? If not, then it is either acidic or basic, looking at those. But that was the take-home exam. It was not exactly, I won't say easy, but it was meant to kind of challenge you because it was a take-home. Now, as I said, this is mostly multiple choice. The only thing that's really not multiple choice would be a titration problem. The titration problem that looks like the titration graph problem. Pretty much all the other ones are multiple choice. You're still guaranteed a 25% shot. A little bit higher if you can reason out some of the wrong answers. There would be 20 questions, mostly from these 2 chapters. So, okay. With that in mind, we can go ahead and start looking at the next chapter. Keep moving along. Okay. Pull this up. Okay. So this chapter is chemical thermodynamics. The main topics are entropy and spontaneity, but we will refresh our knowledge on enthalpy, which is the heat energy. So this first little bit is trying to understand what these terms mean before we actually get into how do we actually calculate these guys. But this, we're really going to start tying things up in a nice clean bow by the end, because when we get to entropy and spontaneity, we're going to relate these back to equilibrium constant K in the end. It's going to be the way you can physically calculate what the K should be at a given temperature using some of these values. You don't have to guess, is K going to go up, is K going to go down? This is going to be the way you actually calculate where does K go when you change the temperature. But, okay. So a quick refresher from general chemistry, that our basic energy unit, our internal energy, we said was delta U. And delta U, the internal energy of a system, was a function of the work and the heat that the system underwent. Then we got into the importance of looking at system versus surroundings. The idea that whatever we are physically measuring, physically observing, trying to calculate is typically our system. The surroundings is whatever that is surrounding it. So depending on how we want to define the system, that could end up being, say, the reaction itself, the individual molecules that react. And the surroundings is the liquid surrounding it, the air surrounding the liquid, the beaker surrounding the liquid, whatever. That could have been the system and the surroundings. Or we could have said the system was the whole solution. And we're looking at how does the heat of the solution change? Or we could have looked at the whole container. Like there's a reaction we've done called fast freezing, where you put a beaker, you dissolve a beaker with a chemical in it. We add water, and I stir it very rapidly, and the beaker is placed on a wet piece of wood, and it freezes to the wood once all is said and done. And this is a case of the heat of the system, the heat from the surroundings flowing into the system. So it pulls the heat out of the surroundings and thus causes the water that the beaker is sitting in to freeze. But in that chapter, we also studied enthalpy of reactions. How did we calculate them? We talked about what it means to be the standard state, how do we calculate the enthalpy of formation of a compound, and how do we calculate the enthalpy of a reaction. So how much heat should be produced by this reaction ended up being just, if you take all the delta H values, it becomes the products times their coefficients minus the reactants times their coefficients. As you see on the reaction, on the equation down below, the delta H of a reaction was the sum of all the products minus the sum of all the reactants. So if I had, for example, I'll go to the doc cam real quick and try to actually remember to switch it over so people can see. If I had a reaction that said, say, CH3OH plus oxygen, and I got to balance this puppy, CO2 and H2O. That's one carbon, 4. That's 2. That's 4. 1 plus. So this ends up being like what? 3/2. So I have to balance that. 2, 3, 2, 4. So the delta H of the combustion of methanol would be whatever the delta H of water times 4 plus the delta H of CO2 times 2. All that subtracted by the delta H of methanol times 2 and the delta H of oxygen times 3. Of course, the delta H of oxygen would end up being 0 because it is a pure element. Does it cost any energy to make methanol? No. To make oxygen? No, because that's the standard elemental state. But that's the big takeaway we need to recall from our general chemistry thermodynamics class. We will go over that more a little bit later, but this reaction, this equation will come back to us. So we need to be able to do that. Now, please note that all the delta H values can be looked up on tables. They are tables in your book. There are tables online. If you write search terms on Wikipedia, will give you a massive table of those. We have books and books and books collecting hundreds of values for almost every conceivable compound. So it's just a matter of looking up the delta H value that you need. Now, a quick reminder, the first law of thermodynamics stated that energy is conserved, that it can neither be created nor destroyed, it is only transferred. And we use that to relate the internal energy to the heat and work of a system. That if the internal energy is changed and you see work going in, the sum of work and heat is the amount of energy transferred. If the internal energy of a system does not change and work goes in, heat must come out. If heat goes in, work must come out, so much that the sum would give you the change or lack thereof. Now, the idea here, if you can calculate the internal energy, you can find out a lot about a reaction. However, enthalpy and the heat and work alone does not state whether a reaction will occur. You cannot simply look at this and say, oh, the delta H is negative, it's going to produce heat, thus the reaction will happen. That will not tell us what will happen. It can point us in the right direction, but there are cases where it won't. So we're going to define spontaneity. I know you can probably think spontaneity, you know, that your friend who always like, oh, let's go bowling, let's go do this, let's go do that. Well, when we talk about a reaction being spontaneous, what we mean is a reaction will occur without any outside intervention. You don't need to suggest, oh, maybe you should react. It will happen. It will happen. It's like a ball. You place it on a incline. It's, unless you put a stopper to keep it in place, it will naturally roll downhill. You don't need to give it a push. It will naturally want to roll. If you pour cream into coffee, given enough, it will mix. You don't have to stir it. It will mix to some extent. Gases will spread. You leave on the stove that produces methane. You got a methane stove. You leave it on. The gas is going to slowly fill up the room. You don't have to do anything for that to happen. All the processes here are spontaneous. Now, some processes will depend on temperature. Like, for example, ice formation or ice melting. If I put water outside in, like, say, Minnesota, it's going to naturally freeze. I put water outside here right now, it's not going to freeze. If I put ice outside in Minnesota, it's going to stay solid. I put ice outside right here, right now, it's going to melt. Depending on the temperature here, we're going to have a spontaneous process one way or the other. All this is a spontaneous process that depends on the temperature, whether we are below zero or above zero. Now, the idea here is that for a spontaneous process, the reverse process will not happen without intervention. Sometimes they're almost impossible to accomplish. It is possible to freeze water when the temperature is not below zero, but you have to have something that, like a refrigerator, that will physically remove the heat from the surroundings, essentially achieving below zero temperatures without the actual weather. In the case of a stone, we can push it up the hill. That's going to require work on your part, pushing it back into place. You could use a centrifuge, or you could use heat to boil out the cream from the coffee. However, that's going to take some amount of energy. Now, it's really hard to separate a smell. I mean, yeah, I guess you could, if you could condense out the various molecules in the air. Like, you could remove oxygen from air by getting the air cold enough, because oxygen, nitrogen, and various things will condense at various temperatures. But some of these are very hard to do. No matter what, though, a non-spontaneous reaction will not happen without external source of energy. So ball will roll down a hill. It's not going to roll back up unless you push it there. Now, the second law of thermodynamics, where you're going to say is simply going to state that for any spontaneous process, that it will have a net increase in the entropy of the universe. So anything that happens without an external energy source will make the universe more random. Entropy is a measure of the degree of randomness or disorder within a system. Like, say you have 6 dice and you have them all facing, so they're 6s are up. If I take the box and I shake it, some of those dice are bound to roll onto different numbers. The randomness here is creating a different pattern. What pattern are you likely to get? That is kind of up to probability there. But it's not gonna, it's very, very, very unlikely to shake the box, roll the dice, and get all 6s again. With that in mind, it's very easy. It's a lot easier to create disorder or randomness than it is to create order. You could flip all the dice back over to 6, but it's going to take energy on your part. You're going to take far more energy on your part than it would take to bump the box, causing the dice to roll. Now, an increase in entropy could be anything like a phase change from solid to liquid or liquid to gas. Those are going to increase the entropy. Just thinking about it. A solid is stuck in one place. It can't really move. When it goes to a liquid, it starts to slosh around. So the randomness goes up. It could be in a lot of different places. A gas, it's no longer contained in a container. It floats around and expands to the size of wherever it's stored. It becomes far more random. An increase in temperature will increase the entropy. When you heat up, the molecules move faster. They bounce around more vigorously, create a far greater degree of randomness. Most times when you dissolve something into solution, you increase the randomness. But that actually depends on how the salt interacts with the water. Sometimes when you dissolve a salt into solution, you could actually decrease the randomness because of how much water actually has to bind to the salt. Anytime you mix two or more substances, like mix two solids together, you're increasing randomness. Mixing two gases together, you're usually going to increase randomness. And anytime you increase the number of molecules of anything, if I double the moles, I'm going to double the randomness, especially for the gas. If I have one gas particle bouncing around in a room, you have limited possibilities. If I suddenly increase it to two gas molecules, I've changed the probabilities far greater. If I have three, we have even more possibilities available. So entropy or randomness will increase as all these things change. Now, entropy, as I said, can be best understood as a probability. Oftentimes, it's a probability that a molecule is acting in a certain way, at a certain place, at a certain time. All molecules can undergo various translational, so it can move left, right, up, down, front, back, based on kinetic energy. Vibrational, so the bonds are stretching and bending and moving. So the molecule, so if it's a compound, the bonds are all moving around. And rotational, the bonds are all spinning. So the molecule is like spazzing out like it's having a seizure and moving all around. The entropy will increase as a greater number of possible movements are possible. And we call these guys microstates. One of the important things, while I will never ask you to ever use this equation, the idea here is that entropy is physically proportional to the Boltzmann's constant times the natural log of the number of microstates. So the number of microstates can directly relate to the entropy measured. Boltzmann's constant is 1.38 times 10 to the 23rd joules per Kelvin. To calculate Boltzmann's constant is actually Avogadro's gas constant, 8.314, divided by Avogadro's number. That's the gas constant divided by Avogadro's number. Now, here's the interesting thing. So, natural log of W, as long as W is not 1, is always going to be a positive number. So, we can physically calculate the entropy of a molecule. Which brings us to the third law of thermodynamics, which states that the entropy of a pure crystalline solid held at 0 degrees Kelvin is 0 joules per mole. So breaking that down, we have a solid. It's kept at the lowest physical possible temperature, 0 Kelvin. We can't go below that. Remember, 0 Kelvin is the bottom. And there is no defects. There's no errors in the crystal. That is the one case when entropy is 0, because that is the one case when the number of possibilities are 1. The molecule is not moving. The molecule has no errors. It is just one possibility held in place. The natural log of 1 is 0. That's the only time entropy for anything will be 0. So from this case, unlike delta H, we cannot get an absolute value. We only look at a change in delta H. But for this case, we can get the absolute entropy of a system, or the absolute entropy of any compound. In fact, there is not really any values that will have an entropy of 0. We said oxygen gas would have an enthalpy, a delta H of 0, because of how we calculate enthalpy. But the entropy of oxygen is non-zero because of the number of microstates possible. Now, if we wanted to calculate an entropy of reaction, all we would have to do is just say that the sum of products minus the sum of reactants. And to keep in mind, if we want the standard, which is the S naught, the S little circle up in the corner, this is done under standard states. This is allowing scientists in multiple different countries to compare all values together, because we can say, oh, I did these all in the same conditions as you, and so we don't have to worry about that. But standard state condition is 1 molar, 1 atmosphere, and 298 Kelvin. If they did this reaction and calculated this value under standard states, you can compare it to anyone else in the world. So this is very similar to delta H, except there is almost no 0 values. Let's see. Before we go any further, let's just calculate some of these guys. I'm going to pull these numbers up. So N2O4 goes to 2NO2. And also look at the zinc, solid plus 2H plus goes to zinc 2 plus and H2. Okay, let's see. 304, 240. Let's see. So 240. I'm writing these down so when I switch over, I don't have to be switching back. Now, there's only one value that is ever going to have a negative enthalpy, or there's only one value that's going to have a 0 enthalpy, and that's protons. And that is simply a definition problem because of solutions and how solutions act. We have to define something as a 0 point because you can never have a cation without an anion. So we defined hydrogen as being a 0. And then the only time you'll have negative entropy at all will have to do with solutions where how it interacts changes. Okay. So with this in mind, first one, delta S of the first reaction is just products times their exponents, so 240.1 times 2, minus reactants times their exponent, times their coefficient. 304.4 times 1. So for the first reaction, we have 1 molecule of gas going to 2 molecules of gas. Even though the 1 molecule is more complicated, N2O4, the net change is a positive 175.8. 175.8. So even though this is more complicated than this, there's 2 of them, so that means more possibilities for randomness. Randomness goes up. This guy, when this reaction goes, we have negative 112.1 because zinc 2 plus actually distracts the water a bit. Distracts the water because the water has to bind with zinc, and it actually decreases the randomness of the water, and that's what's going into to making that negative. Then we have minus the product's 41.63 and 0 times 2. Because there's 0, but there's 2 of them. So negative 112.1 and 130.7 minus 41.63. Now this one, delta S, is negative 23.03. The net effect of this reaction, even though it solid is producing a gas, is actually going down by a little bit. The randomness of this is going down by a little bit. But if you've ever seen this reaction happen, no, it happens pretty easily. There is something else going on here. There's something else going on. So even though the randomness decreases for this guy, this reaction is still what we'd call spontaneous. And this is where we're going to get to, well, we're going to say, when we consider this, we're going to need to consider the whole idea of the entropy of the universe. That number we just calculated, the negative 23, was the localized enthalpy of the system. That enthalpy of the reaction was just the, not enthalpy, the entropy of the reaction is just the entropy of the system. However, to calculate the entropy of the universe, we must add in the entropy of the system and the entropy of the surroundings. For this reaction to be spontaneous, the sum of those two values must be positive. Must be positive. Now, when we calculated enthalpy, the system had very little effect on the overall energy of the surroundings. Because when I have a hot beaker, it heats up maybe localized right around it. But if you ever notice, when we do a bunch of Bunsen burners in the lab, the room doesn't get sweltering hot. The room barely changes a degree, if even that. The overall energy in the room does not go up by much. However, the randomness of the room does go up by a lot. A campfire, if you start a campfire, it may heat up the surrounding area, but it doesn't warm up the whole forest. So these processes are said to be isothermal, meaning they occur without changing the overall temperature. However, we can calculate the entropy of a surroundings by taking the heat of the system and dividing by the temperature. The heat transferred from the to the surroundings as a form of kinetic energy, and thus allowing it to disperse. However, the degree of energy is proportional to the starting temperature. So if the temperature is high, the entropy change is low. If the starting temperature is low, then the entropy change is going to be high. But so the way we can calculate the entropy of the surroundings is just how much enthalpy we have divided by the temperature. How much enthalpy we have divided by the temperature. We have to make it negative to think about enthalpy as leaving the system and going to surroundings. But what we will talk about on Thursday is actively calculating the entropy of the universe. Actually calculating this using our values of delta H and delta S. And then we're going to apply this to spontaneity. That's where we're going to go, but I'm going to leave this here on this practice problem. We're not going to do this just yet. But the idea here is that by looking at both the enthalpy and the entropy of a reaction, you can determine whether a reaction is spontaneous. By looking at the spontaneity, we can learn something about eventually what is our equilibrium constant. What is actually going to, is this going to be a product favored reaction? Is this going to be a reactant favored reaction? Is it going to be somewhere in between and all that? So we're going to start relating these things together by the end. We're going to look at non-standard states. We're going to look at Q again. So all this equilibrium stuff will come back because we'll be looking at if the forward reaction is spontaneous, then what about the reverse reaction? And how is that non-spontaneous? And what values do we have? So we have some stuff to talk about, but we will not get there just yet. We'll stop for now. Thank you for your time. And I'll see you for taking the test when within the week.